German mathematician David Hilbert wrote, "A branch of science is full of life as long as it offers an abundance of problems. A lack of problems is a sign of death." 1900, he presented 23 significant mathematical problems for the 20th century, calling for their solutions. Because of Hilbert's prestige, mathematicians have spent much time tackling problems. His extremely influential speech on the subject began, "Who of us would not be glad to lift the veil behind which the future lies hidden, to cast a glance at the next advances of our science and the secrets of its development during future centuries? What specific goals will there be for which the leading mathematical spirits of the coming generations will strive?" Since then, some mathematicians have accepted the solutions to about 10 problems, while others remain controversial. For example, the Kepler conjecture, part of problem 18, which raised questions about the efficiency of sphere packing, involved a computer-assisted proof, which people needed help verifying. Finally, in 2017, the Forum of Mathematics Pi journal published a formal proof of the Kepler conjecture by a team led by American mathematician Thomas Hales, resolving an unsolved problem for hundreds of years. One of the most famous problems still unsolved today is the Riemann hypothesis, which concerns the distribution of the zeros of the Riemann zeta function, a very wiggly function. David Hilbert remarked, "If I were to awaken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven?" Ben Yandel writes, "Solving one of Hilbert's problems has been the romantic dream of many a mathematician. In the last 100 years, solutions and significant partial results have come from all over the world. Hilbert's list is a thing of beauty, and these well-chosen problems have been an organizing force in mathematics." Chromosomes are thread-like structures, each consisting of a long, coiled DNA molecule wrapped around a protein scaffold. Chromosomes are visible under a microscope during cell division. Human body cells contain 23 pairs of chromosomes, one member of the pair contributed by the mother and one by the father. Sperm and eggs each contain 23 unpaired chromosomes. Fertilization restores the number of chromosomes to 46 in the egg. Around 1865, Austrian priest Gregor Mendel observed that organisms inherit traits via discrete units that we now refer to as genes. However, it was not until 1902 that German biologist Theodore Boveri and American geneticist and physician Walter Sutton independently identified chromosomes as the carriers of this genetic information. While studying sea urchins, Boveri concluded that sperm and egg each had a half set of chromosomes. However, if sperm and egg united to create sea urchin embryos with abnormal numbers of chromosomes, the embryos developed abnormally. Boveri concluded that different chromosomes affected different aspects of the creature's development. Sutton's studies of grasshoppers demonstrated that matched pairs of chromosomes separate during sex cell generation. Not only did Boveri and Sutton suggest that the chromosomes carry parental genetic information, but they also showed that chromosomes may be independent entities that persisted even when they were not visible during various stages of a cell's life, which was counter to the prevailing belief that the chromosomes dissolved during cell division and reformed in the daughter cells. Their work provided a foundation for the new field of cytogenetics, the combination of cytology, the study of cells, and genetics, the science of heredity. Today, we understand that matching chromosomes from parents can exchange small parts during the creation of sperm and eggs, a process known as crossover. This prevents either parent from solely inheriting new chromosomes. Incorrect numbers of chromosomes can lead to genetic disorders. People with Down syndrome have 47 chromosomes. Airplanes are so familiar today that it is hard to imagine life without them. But at the start of the 20th century, no airplane existed, and many believed that humans would never fly. The Wright brothers made the dream of flight a reality in North Carolina in 1903. They were certainly engineers, but they were also scientists and inventors. They had many problems and fundamental questions. How do I create lift? How do you generate sufficient thrust? How do you control flight? How do you make the plane light enough? How do we combine it all? For example, they built a wind tunnel and did fundamental research to discover wing shapes that provided maximum lift. Then, they had to render those shapes as strong, lightweight structures, the bi-wing arrangement of the original Wright Flyer, using wood, fabric, and wire. Then, they had to bend those structures during flight to control the plane. We think their solution today is slightly bizarre. The entire wing warped, and they controlled the warping with their hips. We also find the forward-mounted control surfaces unusual. That's because the Wright brothers started with a blank sheet of paper, with everything unprecedented and unknown. The conventions of rudder, elevator, and ailerons would evolve quickly once the brothers unlocked the core secrets of flight. The entire aircraft was 605 pounds, 275 kilos, empty. How do I get it off the ground? The engine seems primitive by today's standards. At 200 cubic inches, 3.3 litres, and roughly 200 pounds, 91 kilo, it produced just 12 horsepower, 9,000 watts. A small gasoline pan in the engine's air intake was a carburetor. Contact breakers in the cylinders created the spark, and evaporating water cooled the engine. Charles Taylor built it from scratch in a three-way dialogue with the brothers, but it reliably produced 12 horsepower to spin two counter-rotating, hand-carved wooden propellers. Three people could combine many ideas and engineering disciplines to create a working flying machine. Inspiration, curiosity, persistence, and the thrill of discovery powered them through. Russian physiologist Ivan Pavlov insisted that the scientific study of the nervous system and its expressions must be objective, mechanistic, and materialistic in orientation. Pavlov's father is a village priest. Initially, it seemed as though Pavlov would follow in his father's footsteps, but a growing interest in science led him to the University of St. Petersburg, where he earned a degree in physiology. By 1890, Pavlov was director of the Department of Physiology at the university's Institute of Experimental Medicine. The study of digestion, Pavlov's specialty, earned him the Nobel Prize in Physiology or Medicine in 1904. For his experiments, Pavlov chose dogs as subjects. When his work on stomach digestion ended, Pavlov began to study salivation as a necessary part of the digestive process. In 1903, one of the dog handlers in Pavlov's laboratory noticed that the dogs started salivating even before they received their meal. When this observation caught Pavlov's attention, he conducted an experimental investigation into the phenomenon that involves psychic processes. Pavlov investigated the manipulation of external stimuli to regulate behavior. In English, he refers to his most famous example as classical conditioning. The convincing demonstration showed that dogs will learn to salivate even without food when a ringing bell is associated with food offerings. Pavlov claimed that such conditioning was a matter of processes in the nervous system, not the mind. Thus, learning in the dog, and by extension in humans and other animals, was a matter of forming elementary associations that led to forming chains of associations. For many years, Pavlov and his team explored the implications of his model of learning, including how it might explain mental disorders. Generations have grown up knowing that the equation E=mc2 changed the shape of our world, writes author David Bodanis, governing, as it does, everything from the atomic bomb to a television's cathode ray tube to the carbon dating of prehistoric paintings. Of course, part of the equation's appeal, independent of its meaning, is its simplicity. Physicist Graham Farmiloe writes, "Great equations also share with the finest poetry an extraordinary power. Poetry is the most concise and highly charged form of language, just as the great equations of science are the most succinct form of understanding of the aspect of physical reality they describe." In a short article in 1905, Einstein derived his famous E=mc2, also known as the law of mass-energy equivalency, from the principles of special relativity. The formula indicates that a body's mass is a measure of its energy content. The velocity of light in a vacuum, denoted by c, approximates 186,000 miles per second, 299,792,468 meters per second. mc2 governs how radioactive elements constantly convert a portion of their masses to energy. The development of the atomic bomb used this formula to better understand the nuclear binding energy that holds the atomic nucleus together and to calculate the energy released in a nuclear reaction. mc2 explains why the sun shines. The sun fuses 4 hydrogen nuclei, 4 protons, into a helium nucleus, which is less massive than the combined hydrogen nuclei. The fusion reaction converts the missing mass into energy, allowing the sun to heat the Earth and form life. The mass loss, m, during the fusion supplies energy, E, according to Chaki mc2. Every second, fusion reactions convert about 700 million metric tons of hydrogen into helium within the sun's core, releasing tremendous energy. Of all of Albert Einstein's masterful achievements, including the special theory of relativity and the general theory of relativity, the one that won him the Nobel Prize was his explanation of the workings of the photoelectric effect, PE, in which certain frequencies of light shined on a copper plate cause the plate to eject electrons. In particular, he suggested that packets of light, now called photons, could explain the PE. Researchers noted that high-frequency light, like blue or ultraviolet light, could eject electrons, but low-frequency red light did not. Surprisingly, even intense red light did not lead to electron ejection. In fact, the energy of individual emitted electrons increases with the light's frequency, and hence the color. How could the light frequency be the key to the PE? Rather than light exerting its effect as a classical wave, Einstein suggested that the energy of light came in the form of packets, or quanta, and that this energy was equal to the light frequency multiplied by a constant, later called Planck's constant. If the photon was below a threshold frequency, it had no energy to kick out an electron. As a rough metaphor for low-energy red quanta, imagine the impossibility of chipping a fragment from a bowling ball by tossing peas. It just won't work, even if you toss lots of peas. Many observations rely on Einstein's explanation for the energy of the photons. For instance, a given metal has a minimum frequency of incident radiation below which it cannot emit any photoelectrons. Today, numerous devices, such as solar cells, rely on converting light into electric current to generate power. In 1969, American physicists suggested that one could account for the PE without the concept of photons. Thus, the PE did not provide definitive proof of photon existence. Studies of the statistical properties of the photons in the 1970s, however, provided experimental verification of the electromagnetic field's manifestly quantum, non-classical nature. Albert Einstein's special theory of relativity, STR, is one of humankind's greatest intellectual triumphs. At the age of 26, Albert Einstein established one of the fundamental tenets of STR, which asserts that the velocity of light in a vacuum remains unaffected by the motion of the light source and remains constant for all observers, regardless of their movement. This is in contrast to the speed of sound, which changes for an observer who moves, for example, concerning the sound source. This property of light led Einstein to deduce the relativity of simultaneity. Two events occurring simultaneously, as measured by one observer sitting in a laboratory frame of reference, occur at different times for an observer moving relative to this frame. Because time is relative to travel speed, there cannot be a clock in the center of the universe to which everyone can set their watches. An alien who leaves Earth at the speed of light can blink out your entire life and return an hour later to find you dead for centuries. The term relativity partially stems from the notion that our relative states of motion shape the world's appearance, making it relative. Even though we have understood the strange consequences of STR for over a century, students still learn about them with awe and bewilderment. Nevertheless, STR accurately describes nature, from tiny subatomic particles to galaxies. To help understand another aspect of STR, imagine yourself in an airplane traveling at constant speed relative to the ground. We can refer to this as the moving frame of reference. The principle of relativity makes us realize that without looking out the window, you cannot tell how fast you are moving. Since you can't see the passing scenery, you could be in an airplane, stationary on the ground. The Model T Ford debuted in 1908 and featured the first widely used internal combustion engine. The Model T engine was based on the Otto cycle engine, also known as the four-stroke engine, patented in 1861 by Alphonse Beau de Rocher. Given the materials and manufacturing processes available then, an incredible amount of engineering went into making the Model T engine cheap, reliable, and long-lasting. Production ended in 1927, having manufactured over 15 million Model Ts. The engine contained several engineering marvels. Materials engineers improved the Bessemer process to create vanadium steel, which is so strong that some Model T engines still run today. Electrical engineers created the Trembler coil ignition system that helped the engine run on gasoline, kerosene, or ethanol. Engineers also created the thermosiphon system, which moved water through the radiator without a pump. But the real heroes were the manufacturing engineers, who made it possible to produce 2 million cars annually with amazing efficiency, keeping prices low. But if you compare the Model T engine with today's engines, you can see that engineers have achieved a galaxy of improvements since then. The Model T engine had 4 cylinders displacing 2.9 liters, producing only 20 horsepower. Today, motorcycles produce 200 horsepower from 1-liter engines. How is this possible? Engineers created overhead valve trains and high compression ratios to replace the flathead design on Model T. They increased the redline and created fuel injection systems to replace carburetors. They designed much more powerful and precise ignition systems. They created tuned intake and exhaust systems. Only a few technologies have achieved widespread use and high refinement without reconceptualization. After over 100 years of change, all of the core principles of the Model T engine, pistons, valves, spark plugs, water cooling, and gasoline, are still in place. But engineers have fine-tuned and optimized each to create today's compact, reliable, high-power engines. In 1997, Life magazine declared, "The filtration of drinking water, plus the use of chlorine, is probably the most significant public health advancement of the millennium." Adding chlorine, a chemical element, to water is usually an effective treatment against bacteria, viruses, and amoebas, and has played a large role in the dramatic increase in life expectancy in developed countries during the 1900s. For example, waterborne bacterial diseases such as typhoid and cholera became rare in the United States after chlorinating drinking water. Because chlorine remains in the water supply after initial treatment, it protects against contamination from potential pipe leaks. Chlorination was known to be an effective disinfectant in the 1800s, but water chlorination systems for public water supplies were only in continuous use in the early 1900s. Around 1903, the community in Middelkerke, Belgium, used chlorine gas to disinfect drinking water, and in 1908, a water utility in Jersey City, New Jersey, used sodium hypochlorite for water chlorination. In 1910, Brigadier General Carl Rogers Darnell, a U.S. Army chemist and surgeon, used compressed liquefied chlorine gas to purify water for troops on the battlefield. The developed world now uses the basic ideas from his invention of a mechanical liquid chlorine purifier. Major William Lister, an Army scientist, subsequently invented the Lister cloth bag containing sodium hypochlorite to conveniently treat water for troops in the field. The chlorine applied during water disinfection can react with organic compounds to produce trihalomethanes and haloacetic acids, which can potentially cause cancer. However, the risk of these compounds is lower compared to waterborne diseases. Alternatives to chlorination include disinfection with ozone, chloramine, and ultraviolet light. A Darnall Army Medical Center spokesman asserts, "It is safe to say that Darnall's contribution to sanitary water has saved more lives and prevented more sickness than any other single achievement in medicine." In the early part of the 20th century, astronomers worldwide were characterizing and classifying enormous numbers of stars in terms of their colors and spectroscopic lines, expanding on the methods pioneered by Edward Pickering's group at Harvard. When the Danish astronomer Einar Hertzsprung and the American astronomer Henry Norris Russell plotted the spectral classes or temperatures of the stars against their actual brightness, i.e., after correcting their apparent brightness in the sky for their distance from us, they independently noticed an important advance. Most of the stars clustered in a broad sequence from upper left to lower right. Hertzsprung coined the term main sequence to describe this prominent trend among the stars. People started using these plots around 1910 and named them Hertzsprung-Russell (HR) diagrams. Over the next few decades, astronomers began to understand that the main sequence was more than just random clustering. It represented an evolutionary pathway for tracking the age and eventual fate of the stars. Most stars are born when their central pressures and temperatures are high enough for the nuclear fusion of hydrogen atoms into helium. During this hydrogen-fusing phase of its lifetime, a normal star will plot on the main sequence at a position that depends on its mass, with luminous stars a few to 10 times the mass of the Sun, blue giants, on the upper left end of the plot, and dim stars from about 1/10 to 1/2 the Sun's mass, red dwarfs, on the lower right. As stars age and run out of hydrogen fuel, they diverge off the main sequence and eventually die in characteristic, often spectacular ways that again depend on their mass. Astrophysicists such as Arthur Eddington and Hans Bethe later understood the details of stellar interiors, making it possible to predict how stars of specific masses would live and die. Our Sun turns out to be an average mass, middle-aged, main sequence star that appears destined, in about 5 billion more years, to bloat up into a red giant, expel its outer layers into a planetary nebula, and then fade away as a white dwarf. We now know that an atom's dense center is the atomic nucleus, which contains protons and neutrons. However, in the first decade of the 1900s, scientists considered the atom a diffuse web of positively charged material embedded with negatively charged electrons, like cherries in a cake, without knowledge of the nucleus. Ernest Rutherford and his colleagues utterly destroyed this model when they discovered the nucleus after firing a beam of alpha particles at a thin sheet of gold foil. Most of the alpha particles, known today as helium nuclei, went through the foil, but a few bounced straight back. Rutherford said later that this was quite the most incredible event that has ever happened to me. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The cherry cake model of the atom, which was a metaphor for a somewhat uniform spread of density across the gold foil, could never account for this behavior. Scientists would have observed the alpha particles slow down as a bullet fired through the water. They did not expect the atom to have a hard center, like a pit in a peach. In 1911, Rutherford announced a model with which we are familiar today, an atom consisting of a positively charged nucleus encircled by electrons. Given the frequency of collisions with the nucleus, Rutherford could approximate the nucleus's size relative to the atom's size. According to author John Gribbin, the nucleus is 1/100,000th of the diameter of the whole atom, equivalent to the size of a pinhead compared with the dome of St. Paul's Cathedral in London. And since atoms make up everything on Earth, your body and the chair you sit on each consist of 1,000,000 billion times more empty space than solid matter. At very low temperatures, writes science journalist Joanne Baker, some metals and alloys conduct electricity without any resistance. The current in these superconductors can flow for billions of years without losing energy. When electrons become coupled and all move together, avoiding collisions that cause electrical resistance, they approach a state of perpetual motion. In fact, when cooled below a critical temperature, many metals exhibit zero resistivity. This phenomenon, called superconductivity, was discovered in 1911 by Dutch physicist Heike Onnes, who observed that when he cooled a sample of mercury to 4.2 degrees above absolute zero, 452.1 degrees, its electrical resistance plunged to zero. In principle, this means that an electrical current can flow around a loop of superconducting wire forever with no external power source. In 1957, American physicists John Bardeen, Leon Cooper, and Robert Schrieffer determined how electrons could form pairs and appear to ignore the metal around them. Consider a metal window screen as a metaphor for the arrangement of positively charged atomic nuclei in a metal lattice. Next, imagine a negatively charged electron zipping between the atoms and pulling on them to create a distortion. This distortion attracts a second electron to follow the first. They travel together in pairs and encounter less resistance overall. In 1986, Georg Bednorz and Alex Müller discovered a material that operated at a higher temperature of roughly 396 degF, 35 kelvins, and in 1987, a different material was found to superconduct at 297 degrees Celsius, 90 kelvins. Discovering a room temperature superconductor could save energy and develop a high-performance electrical power transmission system. Superconductors also expel all applied magnetic fields, allowing engineers to build magnetically levitated trains. Superconductivity also creates powerful electromagnets in hospital MRI, magnetic resonance imaging scanners. X-ray crystallographer Dorothy Crowfoot Hodgkin, whose research relied on Bragg's law, wrote, "Chemistry and crystals captured me for life." Bragg's law, discovered by English physicists Sir W. H. Bragg and his son Sir W. L. Bragg in 1912, explains the results of experiments involving the diffraction of electromagnetic waves from crystal surfaces. Bragg's law provides a powerful tool for studying crystal structure. For instance, X-rays aimed at a crystal surface interact with the atoms, causing them to re-radiate waves that may interfere with each other. The interference is constructive, reinforcing, for integer values of n, according to Bragg's law. NL Jans 2D sin, Faf. Here, L is the wavelength of the incident electromagnetic waves, e.g. X-rays. D is the spacing between the planes in the crystal's atomic lattice, and Phi is the angle between the incident ray and the scattering planes. For example, X-rays travel down through crystal layers, reflect, and bounce back over the same distance before leaving the surface. The distance traveled depends on the layer separation and the angle at which the X-ray entered the material. For the maximum intensity of the reflected waves to produce constructive interference, the waves must remain in phase. When n is a whole number, both waves remain in phase after reflection. For example, when n=1, we have a first-order reflection. For n=2, we have a second-order reflection. If only two rows were involved in the diffraction, the transition from constructive to destructive interference is gradual as the value of E key changes. However, if interference from many rows occurs, the constructive interference peaks become sharp, with mostly destructive interference between the peaks. You can use Bragg's law to calculate the spacing between atomic planes of crystals and to measure the wavelength of radiation. The study of X-ray wave interference in crystals, known as X-ray diffraction, directly validates the centuries-old notion of a periodic atomic structure in crystals. Even a casual inspection of a map of the southern hemisphere suggests that the coastlines of eastern South America and western Africa fit together like jigsaw puzzle pieces. This same thought occurred to the naturalist explorer Alexander von Humboldt, who, during the early 1800s, found similarities between animal and plant fossils in South America and Western Africa, and common elements between the mountain ranges in Argentina and South Africa. Subsequent explorers saw similarities between fossils in India and Australia. Alfred Wegener, a German geophysicist, meteorologist, and polar explorer, proposed 1912 that the present continents once fused into a single landmass, a concept he named Pangaea, all lands. Expanding upon this theory in his 1915 book, The Origin of Continents and Oceans, Wegener described how Pangaea subsequently split into two supercontinents, Laurasia, corresponding to the present-day Northern Hemisphere, and Gondwanaland, also called Gondwana, Southern Hemisphere, an event now thought to have occurred 180 to 200 million years ago. Until he died in 1930 from heart failure during an expedition to Greenland, Wegener's inability to explain continental drift led to widespread rejection of his concept. In the 1960s, the establishment of plate tectonics, which involved plates in constant motion relative to each other, sliding under other plates, and pulling apart, finally accepted the occurrence of continental drift. Naturalists discovered ancient fossils of the same or similar plants and animals on continents thousands of miles apart, separated by oceans, long before the scientific community acknowledged continental drift. Scientists have discovered the fossil remains of the tropical fern Glossopteris in South America, Africa, India, and Australia, as well as those of the mammal-like reptile family Canamarid in Africa, Asia, and South America. By contrast, some living plants and animals on different continents are very different. For example, all the native mammals in Australia are marsupials and not placental mammals, which suggests that Australia split off from Gondwanaland before placental mammals evolved. Somebody once said about the Greek language that Greek flies in the writings of Homer, writes physicist Amit Goswami. The quantum idea started flying with the work of Danish physicist Niels Bohr, published in the year 1913. Bohr understood the easy removal of negatively charged electrons from atoms and the central position of the positively charged nucleus in the atom. In the Bohr model of the atom, the nucleus was considered to be like our central sun, with electrons orbiting like planets. Such a simple model was bound to encounter issues. For instance, we expect an electron orbiting a nucleus to emit electromagnetic radiation. As the electron loses energy, it should decay and fall into the nucleus. To avoid atomic collapse and explain various aspects of the emission spectra of the hydrogen atom, Bohr postulated that the electrons could not be in orbits at an arbitrary distance from the nucleus. Instead, Bohr limited the electrons to specific permitted orbits or shells. Like climbing or descending a ladder, the electron could jump to a higher rung or shell when it received an energy boost, or fall to a lower shell if one existed. Only when the atom absorbs or emits a photon of a specific energy does the electron hop between shells. Today, the model has many shortcomings and only works for larger atoms. Because the model employs electrons with a definite mass and velocity in orbits with definite radii, it violates the Heisenberg uncertainty principle. Physicist James Trefil writes, "Today, instead of thinking of electrons as microscopic planets circling a nucleus, we now see them as probability waves sloshing around the orbits like water in some donut-shaped tidal pool governed by Schrödinger's equation." Nevertheless, Niels Bohr's outstanding insight in 1913 painted the basic picture of modern quantum mechanical atoms. Matrix mechanics, the first complete definition of quantum mechanics, later replaced the Bohr model and better described the observed transitions in the energy states of atoms. Albert Einstein once wrote that all attempts to obtain a deeper knowledge of the foundations of physics seem doomed to me unless the basic concepts are in accordance with general relativity from the beginning. In 1915, 10 years after Einstein proclaimed his special theory of relativity, which suggested that distance and time are not absolutes, and that one's measurements of the ticking rate of a clock depend on one's motion about the clock, Einstein gave us an early form of his general theory of relativity, GTR, which explained gravity from a new perspective. Specifically, Einstein proposed that space-time masses cause space-time curvature, not a force like other forces. Although we now know that GTR does a better job describing motions in high gravitational fields than Newtonian mechanics, such as Mercury's orbit around the Sun, Newtonian mechanics is still useful in describing the world of ordinary experience. To better understand GTR, consider that wherever a mass exists in space, it warps space. Imagine a bowling ball sinking into a rubber sheet. This is a convenient way to visualize what stars do to the fabric of the universe. If you place a marble into the depression formed by the stretched rubber sheet and give it a sideways push, it would orbit the bowling ball for a while, like a planet orbiting the Sun. The bowling ball's warping of the rubber sheet is a metaphor for a star warping space. We can use GTR to understand how gravity warps and slows time. In several circumstances, GTR also appears to allow time travel. Einstein additionally suggested that gravitational effects move at the speed of light. Therefore, if we were to abruptly remove the Sun from the solar system, the Earth would only depart from its orbit around the Sun for approximately 8 minutes, the duration it takes for light to reach the Earth. Today, many physicists believe that gravitation must undergo quantization, transforming into particles known as gravitons, similar to how light manifests as photons, tiny quantum packets of electromagnetism. The mathematics involved in string theory, writes mathematician Michael Atiyah, in subtlety and sophistication, vastly exceeds previous uses of mathematics in physical theories. String theory has led to many amazing mathematical results in areas far removed from physics. To many, this indicates that string theory must be on the right track. String theory is 21st century physics that accidentally fell into the 20th century, writes physicist Edward Witten. Various modern theories of hyperspace suggest that dimensions exist beyond the commonly accepted dimensions of space and time. For example, the Kaluza-Klein theory of 1919 made use of higher spatial dimensions in an attempt to explain electromagnetism and gravitation. Among the most recent formulations of these concepts is superstring theory, which predicts a universe of 10 or 11 dimensions. 3 dimensions of space, 1 dimension of time, and 6 or 7 more spatial dimensions. According to many theories of hyperspace, nature's laws become simpler and more elegant when expressed in these several extra spatial dimensions. In string theory, inconceivably tiny, essentially one-dimensional entities called strings can model some of the most basic particles, like quarks and electrons. While strings may appear as mathematical abstractions, it's important to remember that atoms, once considered unreal mathematical abstractions, eventually transformed into observables. Today, strings are too small to observe directly. In some string theories, the loops of string move about in ordinary 3 space, but they also vibrate in higher spatial dimensions. As a simple metaphor, think of a vibrating guitar string whose notes correspond to different particles, such as quarks and electrons, or the hypothetical graviton, which may convey the force of gravity. String theorists claim that various higher spatial dimensions are compactified, tightly curled up, in structures known as Calabi-Yau spaces, so the extra dimensions are invisible. In 1984, Michael Green and John H. Schwartz made additional breakthroughs in string theory. Hydrogen bonds are the secret adhesive of the living world. They hold together DNA strands, help determine protein shapes, and occur in every kind of carbohydrate molecule. For example, the active sites of receptors and enzymes almost invariably feature key hydrogen bonds in the protein structure and with the binding substrate molecules. American chemist Maurice Loyal Huggins was the first to suggest the concept of hydrogen bonds. His work inspired his colleagues, Wendell Mitchell Latimer and Worth Huff Rodebush, to publish a 1920 paper using hydrogen bonds to explain the properties of certain liquids. Since then, almost 100 years of work have yet to reveal their secrets. So, what's a hydrogen bond? That's a challenging question to answer. Even the best minds, such as American chemist Linus Pauling, have found plenty to occupy themselves here. Hydrogen bonding is partly the attraction between a positively charged hydrogen atom and a negatively charged atom, such as nitrogen or oxygen, on a nearby molecule. These don't have to be full charges. Oxygen and nitrogen atoms usually have extra electron density, making them clumps of partial negative charge. However, hydrogen bonds are directional, meaning that the attraction largely vanishes if they point in the wrong direction. When the hydrogen attaches to an electron-rich atom like oxygen, it becomes stronger, resembling a ghostly form of a standard single bond. A wide range of chemistry contains oxygen-hydrogen and nitrogen-hydrogen compounds, which play a crucial role in the behavior of many biomolecules. Water is the best example, with 2 hydrogen atoms attached to a single oxygen atom. Water molecules are excellent hydrogen bond donors and acceptors simultaneously, making it a unique substance. It has a much higher boiling point than such a tiny molecule should, and it freezes into a hydrogen-bonded crystal lattice that's actually less dense than the liquid. Most liquids do not contain ice that floats. If we could get into our time machine, go back to 1912, and stand on the deck of the sinking Titanic, we'd see something overhead that marked the beginning of a new era in communication. The Titanic had 2 masts, one at either end of the ship, with a long wire stretching between them. This was the antenna for a 5,000-watt spark gap radio, and the Titanic used it to send out Morse code distress signals. The map of the Titanic showed the location of the radio. Because of that disaster, the Radio Act of 1912 required ships to monitor for distress calls 24 hours a day and set up a system for the US government to license radio stations. By 1920, the first AM radio station was broadcasting in the United States, KDKA in Pittsburgh, PA. World War I accelerated the mass production of vacuum tubes between 1912 and 1920. Vacuum tubes allowed electrical engineers to create amplifiers for radio transmitters and receivers. Once engineers created the necessary equipment, the popularity of radios skyrocketed. Everyone had to have a radio. By 1922, there were more than 1 million radio receivers in the US. Hundreds of organizations, newspapers, colleges, department stores, and individuals had created radio stations. The golden age of radio was born. NBC started in 1926 and CBS started in 1927. Government regulations changed to make the advertising model possible on radio. With a revenue stream in place, broadcasters had a good reason to expand and plenty of money to pay for content. This whole story is fascinating. The war led to the invention of tubes, which led to the development of radios. The result was an entirely new way of thinking, instantaneous, electronic, free mass media for millions of people through nationwide networks funded by advertising. None of that existed in 1920. By 1930, nearly half of American homes had radios. With the Great Depression starting, radio provided inexpensive news and entertainment. Electrical engineering has created massive societal change. Despite the horrible prejudice they faced, several women have fought against the establishment and persevered in mathematics. Albert Einstein described Emmy Noether, a German mathematician, as the most significant creative mathematical genius since the beginning of women's higher education. In 1915, while at the University of Göttingen, Germany, Noether's first significant mathematical breakthrough was in theoretical physics. Noether's theorem, in particular, dealt with symmetry relationships in physics and their relation to conservation laws. This and related work aided Einstein when he developed his general theory of relativity, which focused on the nature of gravity, space, and time. After Noether had received her PhD, she attempted to teach at Göttingen, but her opponents said that men could not expect to learn at the feet of a woman. Her colleague David Hilbert responded to her detractors. "I do not see that the candidate's sex is against her admission as a private doesn't licensed lecturer. After all, the University Senate is not a bathhouse." Noether's contributions to non-commutative algebras where the order of term multiplication influences the results, are also well known. She is most famous for studying chain conditions on ring ideals. In 1921, Noether published Ideal Theory in Ringbereichen, which is important for developing modern abstract algebra. This area of mathematics examines the general properties of operations and often unifies logic and number theory with applied mathematics. Unfortunately, the Nazis dismissed her mathematical achievements at the University of Göttingen in 1933 due to her Jewish heritage. She fled Germany and joined the faculty at Bryn Mawr College in Pennsylvania. According to journalist Siobhan Roberts, Noether made weekly trips to lecture at Princeton's Institute and to visit her friends Einstein and Hermann Weyl. Her influence was far-reaching, and many of her ideas appeared in papers written by students and colleagues. Nobel Prize winner people recognize Albert Einstein as one of the greatest physicists and most important scientists of the 20th century. He proposed the special and general theories of relativity, revolutionizing our understanding of space and time. He also made major contributions to the science of quantum mechanics, statistical mechanics, and cosmology. Physics has come to dwell at such a deep distance from everyday experiences, writes Thomas Levinson, author of Einstein in Berlin, that it's hard to say whether most of us would be able to recognize an Einstein-like accomplishment should it occur today. When Einstein first came to New York in 1921, thousands lined the street for a motorcade. Try to imagine any theoretician today getting such a response. It's impossible. The emotional connections between the physicist's conception of reality and the popular imagination have weakened greatly since Einstein. According to many scholars I consulted, there will never be another individual on par with Einstein. Levinson suggested, it seems unlikely that science will produce another Einstein in the sense of a broadly recognized emblem of genius. Today's model's sheer complexity restricts almost all practitioners to specific aspects of the problem. Unlike today's scientists, Einstein required little or no collaboration. Einstein's paper on special relativity contained no references to others or prior work. Bran Ferren, co-chairman and chief creative officer of the Applied Minds Technology Company, affirms that the idea of Einstein is perhaps more important than Einstein himself. Not only was Einstein the greatest physicist in the modern world, but he was an inspirational role model whose life and work ignited the lives of countless other influential thinkers. The total of their contributions to society and the contributions of the thinkers they will inspire will greatly exceed those of Einstein himself. Einstein created an unstoppable intellectual chain reaction, an avalanche of pulsing, chattering neurons and memes that will ring for eternity. The electromagnetic spectrum refers to the vast range of electromagnetic, EM, radiation frequencies. Energy waves, which can propagate through a vacuum and contain perpendicular oscillating electric and magnetic field components, compose the electromagnetic spectrum. The frequency of the waves identifies different portions of the spectrum. In order of increasing frequency and decreasing wavelength, we have radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays. We can see light with wavelengths between 4,000 and 7,000 angstroms, where an angstrom equals 10 to 10 meters. Electrons moving back and forth in transmission towers can generate radio waves with wavelengths ranging from several feet to many miles. If we represent the electromagnetic spectrum as a 30-octave piano, in which the radiation wavelength doubles with each octave, visible light occupies only part of an octave. If we wanted to represent the entire radiation spectrum detected by our instruments, we would need to add at least 20 octaves to the piano. Extraterrestrials may have senses beyond our own. Even on Earth, we find examples of creatures with increased sensitivities. For example, rattlesnakes have infrared detectors that give them heat pictures of their surroundings. To our eyes, both the male and female Indian lunar moths are light green and indistinguishable, but they perceive the ultraviolet range of light. Therefore, to them, the female looks quite different from the male. When lunar moths rest on green leaves, other creatures find it difficult to see them, but they perceive each other as brilliantly colored. Bees can also detect ultraviolet light. In fact, many flowers have beautiful patterns that bees can see to guide them to the flower. Human perception completely hides these attractive and intricate patterns. To our eyes, male and female lunar moths are light green and indistinguishable. But the lunar moths perceive light in the ultraviolet range, and the female looks quite different from the male. In 1907, the American physician Franklin C. Clark wrote, "Three notable events characterize the history of medicine, each of which in turn has completely revolutionized the practice of surgery. The first event involved using ligatures to stem the blood flow during surgeries, for example, as performed by the French surgeon Ambroise Paré. According to several Americans, the second involved decreasing pain through general anesthetics, such as ether. The third concerned antiseptic surgery, promoted by British surgeon Joseph Lister. Lister's use of carbolic acid, now called phenol, to sterilize wounds and surgical instruments dramatically reduced post-operative infections. Louis Pasteur's work on the germ theory of disease stimulated Lister to use carbolic acid to destroy microorganisms. In 1865, he successfully treated a compound fracture of the leg, where the bone juts through the skin, by dressing the leg with cloths dipped in carbolic acid solutions. Lister published his findings in the paper Antiseptic Principles of the Practice of Surgery in 1867. Lister was not the first to suggest various forms of sterilization. For example, William Henry, a British chemist, advised sterilization of clothing through heating, and Ignaz Semmelweis, a Hungarian obstetrician, advocated hand-washing to prevent the spread of disease by physicians. Nevertheless, Lister's sloping of carbolic acid onto open wounds usually prevented the development of the horrific infections that so often occurred in hospitals during his time. His writings and talks convinced medical professionals of the need for antiseptics. People usually apply antiseptics directly to the body's surface. Modern methods for preventing infections focus more on aseptic methods that involve sterilization to remove bacteria before they come near a patient, e.g., equipment disinfection and surgeons' masks. Today, we also use antibiotic drugs to combat internal infections. In 1891, William Halsted pioneered the use of rubber gloves in surgery. An Austrian priest, Gregor Mendel, studied the inheritance of easily identifiable traits in pea plants, such as color or wrinkling, and demonstrated that mathematical laws and ratios could explain this inheritance. Despite not receiving recognition during his lifetime, the laws he discovered laid the groundwork for genetics, the science that studies heredity and organism variation. In 1865, Mendel reported on his studies of more than 20,000 pea plants, conducted over 6 years, which led him to formulate his laws of genetics. He observed that organisms inherit traits via discrete units that we now refer to as genes. This finding was in contrast to other popular theories of his time, such as an individual inheriting a smooth blend of traits from the parents, or inheriting acquired characteristics from their parents, such as a son having large muscles simply because his father lifted weights. For example, consider that in peas, each plant has 2 alleles, versions of each gene, and the offspring inherit 1 allele from each parent. The offspring randomly inherit 1 gene from each parent. If the offspring inherits a yellow and a green seed gene, the yellow gene may predominate, but the green gene remains present and consistently and predictably transmits to the plant's descendants. Today, medical geneticists aim to understand how genetic variations affect human health and disease. For example, a mutation, change, in a single gene that affects the membranes of cells causes cystic fibrosis, which includes difficulty breathing, among other symptoms. The ideas associated with Mendel's genetics eventually led to a better understanding of genes and chromosomes, composed of a DNA molecule containing many genes, along with the potential to cure many diseases and shape the evolution of the human species. Researchers have even inserted human genes into bacteria to produce large quantities of insulin for diabetic individuals. The periodic table is the undisputed centerpiece of chemistry. Its arrangement contains a wealth of hard-earned knowledge about atomic structure, reactivity, bonding, and other crucial concepts. The building blocks of our world are all there, organized in a way that shows their deepest relationships. German chemist Lothar Meyer and English chemist John Alexander Rayner Newlands were two of the first to realize, independently, that arranging the known elements by their atomic weights revealed underlying patterns. Elements with similar behavior tended to cluster together, such as sodium and potassium, soft, highly reactive metals. In Russia, chemist Dmitry Ivanovich Mendeleev, unaware of Meyer and Newlands' work, was thinking along the same lines, and in 1869, he presented his own arrangement based on atomic weights and the number of bonds the various elements tend to form. It not only had all the known elements, but it also boldly included gaps where new ones were predicted to exist. Their discovery and successful prediction of their properties was powerful evidence that Mendeleev had it right. Dutch physicist Antonius van den Broek and English physicist Henry Gwyn Jeffreys Moseley suggested ordering modern tables by increasing atomic number, the number of protons in the nucleus. The columns, called groups, represent increasing numbers of electrons in each atom's outermost shell, called an orbital. From just one electron on the far left column, reactive sodium and its alkali metal group members, to the unreactive noble gases on the far right with their perfectly filled orbitals. Then, a new row, called a period, starts, with a heavier alkali metal on one end going over to a heavier noble gas. The heavier elements demonstrate the greater number of electrons that go into the outer orbitals, and the table spreads out accordingly. It's no exaggeration to say that many of the advances in chemistry over thousands of years led up to this. Understanding how the elements differ and why has been one of the great works of the human race. German mathematician Georg Cantor founded modern set theory and introduced the mind-boggling concept of transfinite numbers that can denote the relative sizes of an infinite collection of objects. The smallest transfinite number is called Aleph naught, written as 0, which counts the number of integers. If the number of integers is infinite, with 0 members, are there any higher levels of infinity yet? It turns out that even though there are an infinite number of integers, rational numbers, numbers that can be expressed as fractions, and irrational numbers, like the square root of 2 that cannot be expressed as a fraction, the infinite number of irrationals is in some sense greater than the infinite number of rationals or integers. Similarly, there are more real numbers, including rational and irrational numbers, than integers. Before becoming a fundamental theory, Cantor's shocking concepts about infinity drew widespread criticism, which likely contributed to his bouts of severe depression and multiple institutionalizations. Cantor also equated his concept of the absolute infinite, which transcended the transfinite numbers, with God. He wrote, "I entertain no doubts as to the truths of the transfinites, which I recognized with God's help, and which, in their diversity, I have studied for more than 20 years." In 1884, Cantor wrote to Swedish mathematician Gösta Mittag-Leffler, explaining that he was not the creator of his new work, but merely a reporter. God had provided the inspiration, leaving Cantor only responsible for the organization and style of his papers. Cantor said that transfinites were real because God had told me so, which would have diminished God's power had God only created finite numbers. Mathematician David Hilbert described Cantor's work as the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. One drop of ink may make a million think, says an old proverb. The Austrian physicist Ludwig Boltzmann was fascinated by statistical thermodynamics, which focuses on the mathematical properties of large particles in a system, including ink molecules in water. In 1875, he formulated a mathematical relationship between entropy S, roughly the disorder of a system, and the number of possible states of the system W in a compact expression, S(k log W). Here, K represents Boltzmann's constant. Consider a drop of ink in water. Kinetic theory states that molecules constantly move randomly and constantly rearrange themselves. We assume that all possible arrangements are equally probable. Since most ink molecular arrangements do not correspond to a drop of clustered ink molecules, we typically do not observe such a drop. Mixing happens spontaneously because there are more mixed arrangements than unmixed ones. A spontaneous process occurs because it produces the most probable final state. We can calculate the entropy using the formula S(k log W and understand why the more states that exist, the greater the entropy. A state with a high probability, e.g., a mixed ink state, has a large value for the entropy, and a spontaneous process produces the final state of greatest entropy, another way of stating the second law of thermodynamics. Using the thermodynamics terminology, we can say that several ways W, number of microstates, exist to create a particular macrostate, in our case, a mixed state of ink in a glass of water. Although Boltzmann's idea of deriving thermodynamics by visualizing molecules in a system seems obvious today, many physicists of his time criticized the concept of atoms. Repeated clashes with other physicists, combined with an apparent lifelong struggle with bipolar disorder, may have contributed to the physicist's suicide in 1906, while on vacation with his wife and daughter. His tombstone in Vienna bears his famous entropy equation. If you want to look under the hood of chemistry and see what makes things work, consider studying thermodynamics. It measures energy changes, the driving force for all chemical processes. Credit here goes to American scientist Josiah Willard Gibbs, whose theoretical insights and outstanding mathematical ability turned thermodynamics into a precise scientific tool with applications in every possible area of chemistry, physics, and biology. In 1876, he published his work on chemical systems and the free energy of reactions, now called Gibbs free energy, or G in his honor. When a system transitions from one state to another, chemically through a reaction, or physically through melting or boiling, it exchanges work with its surroundings, such as the heat it releases, resulting in a change in G, also known as delta G. Chemical reactions that spontaneously give off energy show a negative G. A fire is a perfect example. Reactions with even larger negative G values, such as the thermite reaction or the decomposition of nitroglycerin, can be dangerously energetic. In contrast, reactions with a positive G, photosynthesis in plants for example, require the addition of external energy, such as sunlight. The other key thing to know about G is that it comprises two parts, enthalpy and entropy. Enthalpy, designated by the letter H, can be thought of as a pure measure of heat and energy, while entropy, S, is related to the disorder and the reactant's degrees of freedom, i.e., how many different ways they can move and vibrate. Chemists constantly think in these terms, gaining significant insight into reactions by considering all these factors. Some chemical reactions are spontaneous, even though they get cold and soak up heat from their surroundings, like an instant cold pack. This can happen because the entropy of the final state is so much higher, S, than that of the starting materials, cancelling out an unfavorable enthalpy change, H, and giving an overall favorable G. If both H and S are large and negative, though, you have an explosion in the making. Imagine that the year is 1850 and you want to talk to someone. You have one option. You can travel and meet with that person face to face, which could take days or weeks, depending on distance. An alternative is a handwritten letter. By 1850, the telegraph system had started to expand. However, the simple act of talking to someone still requires a face-to-face meeting. Enter the telephone. In 1876, Alexander Graham Bell received his patent for the telephone. The device was incredibly simple: a carbon granular microphone and a speaker. To connect two telephones, all you needed was a copper wire and a small source of electric current, like a battery. With this innovation, two people talked to each other at a distance for the first time. How did engineers scale this up? The central office was the first innovation. In a town, copper wires ran from each home or business to the central office. An operator could connect any line to any other line in town. We've added wires to connect the town to the next one. At that point, anyone in the two towns could communicate. As additional towns connected, regional central offices were formed. Eventually, trunk lines spanned the country and then the world, and now everyone could connect to everyone else. Engineers developed mechanical switches to replace human operators. The telephone dial told the switches what to do. As a result, the cost of calling fell. Engineers created much smaller computers to replace the mechanical switches, making touch-tone dialing possible. The cost of making a call fell again. Engineers turned voice signals into digital bits and sent the bits through fiber optic cables, drastically reducing costs and increasing capacity. Next, engineers developed voice over IP, VoIP, enabling routing calls via the internet. Internet telephony was born, and calling became free on many VoIP networks. The success story for engineering: taking something that used to be impossible and eventually making it free. Life cannot exist without enzymes. In living cells, thousands of chemical reactions occur. New cells are replacing the old ones. Simple molecules link to form complex ones. Digestion transforms food into energy. Waste materials are disposed of. Cells reproduce. We collectively refer to these build-up and breakdown reactions as metabolism. For each reaction to occur, a certain degree of energy is required, activation energy. Without such energy, these reactions would not occur spontaneously. The presence of these enzymes, usually proteins or RNA enzymes, reduces the activation energy required for these reactions and increases their rate by millions. Enzymes neither consume nor undergo chemical changes during the process. Each chemical reaction in the body is a component of a pathway or cycle, and most enzymes are highly specific and act on only a single substrate, reactant, in the pathway to produce a product in the metabolic sequence. Most of the more than 4,000 enzymes in living cells are proteins with a unique three-dimensional configuration, the shape of which accounts for their specificity. Commonly, we name an enzyme by adding the suffix ase to the root name of the substrate it acts on, although chemically oriented literature uses more specific and descriptive names. Saliva and plant extracts could break down starch into simple sugars and secretions in the stomachs of digested meat in the late 17th and early 18th centuries. Wilhelm Kuhne, a German physiologist, was the first to coin the name enzyme in 1878 to refer to trypsin, a protein-digesting enzyme he had discovered. And, in 1897, Eduard Buchner at the University of Berlin first demonstrated that digestive enzymes could function outside living cells. In 1926, working with the jack bean, James Summer at Cornell University isolated and crystallized the first enzyme, urese, and provided conclusive proof that it was a protein. Summer was the co-recipient of the 1946 Nobel Prize in Chemistry. The American inventor Thomas Edison, best known for developing the light bulb, once wrote, "To invent, you need a good imagination and a pile of junk." Edison was not the only person to have invented a version of the incandescent light bulb, a light source that uses heat-driven light emissions. Other equally notable inventors include Joseph Swan of England. However, the combination of factors he helped to promote, a long-lasting filament, the use of a higher vacuum within the bulb than others were able to produce, and a power distribution system that would make the light bulb practical in buildings, streets, and communities, is what best remembers Edison. In an incandescent light bulb, an electric current passes through the filament, heating it to produce light. A glass enclosure prevents the oxygen in the air from oxidizing and destroying the hot filament. One of the greatest challenges was finding the most effective material for the filament. Edison's carbonized bamboo filament could emit light for more than 200 hours. Today, people often use tungsten wire filaments and fill the bulb with an inert gas like argon to prevent the filament's material from evaporating. Coiled wires improve efficiency, and the filament in a typical 60-watt, 120-volt bulb is actually 22.8 inches, 580 millimeters, in length. A bulb can last surprisingly long when operated at low voltage. For example, the Centennial light in a California fire station has been burning almost continually since 1901. Generally, incandescent lights are inefficient, as they convert about 90% of the consumed power to heat instead of visible light. Although today, more efficient forms of light bulbs, e.g. compact fluorescent lamps, are starting to replace incandescent bulbs. The simple incandescent bulb once replaced the soot-producing and more dangerous lamps and candles, changing the world forever. 1878, at the Paris World's Fair, visitors marveled at the Yablochkov arc lamps, patented by Pavel Yablochkov in 1876, powered by the Zenobé Gramme dynamos. This was an example of an early commercial high-voltage power system, the kind of power grid that exists invisibly behind the scenes worldwide today. It is possible to imagine a society with no power grid, where every home and business generates its own power on site. But this approach has efficiency problems. When purchasing fuel, a large power plant can realize economies of scale and apply significant resources to emission controls. Advanced technologies like nuclear power are not possible without a big power plant. And site-specific power sources like hydropower, solar power, and wind turbines only make sense if a grid exists. A power grid can also improve reliability. When a big power plant needs to go offline for maintenance, other power plants in the area use the grid to make up the load. Amazingly, the power grid has only two key components: wires and transformers. Transformers can multiply voltages up and down. For long-distance transmission, transformers boost the voltage to 700,000 volts or more. Once the power arrives at its destination, transformers step down the voltage. It might travel at 40,000 volts in a community and then at 3,000 volts in a neighborhood. At your house, a final transformer brings it to 240 and 120 volts for use in your wall outlets and light switches. The grid has room for improvement, and there are occasional instances of widespread blackouts. On a sweltering summer day with the whole grid running at peak loading, a failure in a key transmission line can cause an irresolvable problem. Other lines try to pick up the load from the failed line, but they overload and fail. A ripple effect can leave several states dark. Engineers are also working on new architectures to avoid this problem. Once perfected, the grid will be even more invisible. It is hard to imagine nothing, physicist James Trefil writes. For most of history, the human mind sought to fill empty space with a material known as the ether. The idea was that the emptiness between celestial objects was filled with a kind of tenuous jello. In 1887, physicists Albert Michelson and Edward Morley conducted pioneering experiments to detect the luminiferous ether thought to be pervading space. The ether idea was not too crazy. After all, water waves travel through water and sound travels through air. Didn't light also require a medium to propagate, even in an apparent vacuum? To detect ether, the researchers split a light beam into two beams that traveled at right angles. The researchers reflected both beams back and recombined them to create a striped interference pattern, dependent on the travel duration in both directions. When one of the light beams, which had to travel into the ether wind, slowed relative to the other beam, the interference pattern should change, indicating that the Earth was moving through an ether. Michelson explained the idea to his daughter. Two beams of light race against each other, like two swimmers, one struggling upstream and back, while the other, covering the same distance, just crosses and returns. If there is any current in the river, the second swimmer will always win. We minimized vibrations by floating the apparatus on a pool of mercury and rotated it relative to the Earth's motion to make such fine measurements. The experiment, the most famous failed experiment in physics, found no significant change in the interference patterns, suggesting that the Earth did not move through an ether wind. This finding helped persuade other physicists to accept Einstein's special theory of relativity. I know of no mathematics subject that has intrigued children and adults as much as the idea of a fourth dimension, a spatial direction different from all the directions of our everyday three-dimensional space. Theologians have speculated that the afterlife, heaven, hell, angels, and our souls could reside in a fourth dimension. Mathematicians and physicists frequently use the fourth dimension in their calculations. It's one of the important theories describing our universe's very fabric. The tesseract is the four-dimensional analog of the ordinary cube. People more commonly refer to cube analogs in other dimensions as hypercubes. The trail of a cube moving into the fourth dimension produces a tesseract, just as one can visualize a cube by dragging a square into the third dimension and observing the shape it traces through space. Computer graphics often aid mathematicians in developing a better intuition for higher dimensional objects, despite the challenge of visualizing a cube shifting in a direction perpendicular to all three of its axes. Square faces bound a cube, while cubical faces bound a tesseract. We can write down the number of corners, edges, faces, and solids for these kinds of higher dimensional objects. British mathematician Charles Howard Hinton first used the term tesseract in his book A New Era of Thought in 1888. Hinton, a bigamist, was also famous for his set of colored cubes that he claimed could help people visualize the fourth dimension. People believed that the Hinton cubes, used at seances, could help people glimpse the ghosts of deceased family members. If you go to any large power plant today, one of the landmarks will be a huge steam turbine larger than a bus. You find steam turbines on aircraft carriers and nuclear submarines too. With the steam turbine, engineers were able to reconceptualize the extraction of power from steam and thus abandon pistons. Let's get in our time machine and return to the Titanic's engine room in 1912. In this scenario, steam from over 100 massive coal-fired boilers fuels 3 steam engines, powering 3 propellers. 2 steam engines are gigantic piston machines producing 30,000 HP, 22 million watts, each, and the third is a steam turbine producing about half that. What we witness here is a period of transition. Sir Charles Parsons first invented steam turbines in 1890, and while they had not yet reached perfection, they were soon to replace pistons in extracting rotational energy from steam. The basic idea behind a steam turbine is extremely simple. The expanding steam turns a series of vanes attached to a shaft. As the steam expands, the progressively larger vanes capture its energy. Compare that process to the Titanic's piston engines, which use 3 cylinders of increasing size. The steam first expands in the smallest cylinder. Then, it flows to the next cylinder, somewhat larger in size, to extract more power from the less dense exhaust of cylinder 1. Next, it moves on to the third cylinder, which is even larger. This worked, but it made for a large, heavy piece of equipment. One steam piston engine on the Titanic weighed 1,000 tons. A steam turbine does the same job but is much smaller, lighter, and more efficient than an equivalent steam piston engine. Because of these advantages, modern steam turbines appear in almost every major coal-fired and nuclear power plant today. Instead of just 3 expansion chambers, the steam turbine can have many stages of vanes that increase in size to extract as much power as possible. This shows how engineers switch to completely new concepts to get better results. Despite his artistic temperament, William James submitted to his father's wishes and pursued his education as a physician. He never practiced, however, and after a period of existential struggle, he accepted an appointment as a lecturer at Harvard. He pioneered the new field of psychology in America and wrote what proved to be the most influential text of his era, The Principles of Psychology. After writing The Principles of Psychology for 12 years and publishing it in 1890, he wrote to a friend, "Psychology is a damnable subject." In Principles, James described psychology as the science of mental life. He wrote that the point of scientific psychology was to help us understand that consciousness and our minds evolved to help us adapt and survive in the world. Thus, what consciousness does is more important than what it is or contains. What is the most effective method for studying the mind? The first laboratory psychologists in Germany used refined mechanical instruments, such as the hip chronoscope, to measure mental reactions. James rejected this approach, believing that one could never understand the complexity of human mental life by adding up its contents or measuring the speed of reactions. James offered an alternative view of consciousness. In a beautiful and enduring metaphor, he said consciousness is like a dynamic and ever-changing stream. A person, he wrote, could never step into the same river twice. Thus, no instrument could ever capture this experience. James also wrote about habit, calling it the flywheel of life. He proposed a theory of emotions that says feelings follow behavior, now known as the James Lange theory of emotions. Danish physician Carl Lange made the same suggestion independently and simultaneously. James also argued for a pragmatic, pluralistic view of truth. Those things are true, he argued, that help us in life. James and his book have greatly influenced American psychology's development. To illustrate his breadth, his obituary headline in the New York Times is worth noting. William James dies. Great psychologist, brother of novelist and foremost American philosopher, was 68 years old. A longtime Harvard professor, the virtual founder of modern American psychology, and exponent of pragmatism, dabbled in spooks. According to neurobiologist Gordon Shepherd, the neuron doctrine is one of the great ideas of modern thought, comparable to quantum theory and relativity in physics, and the periodic table and the chemical bond in chemistry. Having been born in microscopy studies in the late 1800s, the neuron doctrine posits that distinct cells called neurons serve as the functional signal units of the nervous system, and that neurons connect to one another in several precise ways. German anatomist Wilhelm von Waldeyer-Hartz formally stated the doctrine in 1891, drawing from the observations of Spanish neuroscientist Santiago Cajal, Italian pathologist Camillo Golgi, and other scientists. Cajal improved upon the Golgi's special silver stains, allowing them to better microscopically visualize the incredible detail of cell-branching processes. While modern scientists have discovered exceptions to the original doctrine, most neurons contain dendrites, a soma, cell body. An axon can extend up to 3 feet or 1 meter in length. In many cases, signals may propagate from one neuron to another by neurotransmitter chemicals that leave the axon of one neuron, travel through a tiny junction space called a chemical synapse, and then enter the dendrite of an adjacent neuron. When signals impinge on a neuron and cause a sufficiently large net excitation, the neuron generates an action potential, a brief electrical pulse that travels along the axon. Electrical synapses, called gap junctions, also connect directly between neurons. Sensory neurons carry signals from sensory receptor cells in the body to the brain. Motor neurons transmit signals from the brain to muscles, and glial cells provide structural and metabolic support to the neurons. While adult neurons do not reproduce, new connections between neurons can form throughout life. Approximately 100 billion neurons can have more than 1,000 synaptic connections. Multiple sclerosis results from insufficient myelin, chemical insulation, around the axons. Parkinson's disease is associated with a lack of the neurotransmitter dopamine, normally produced by certain neurons in the midbrain. Science journalist Robert Adler writes, rabies, smallpox, yellow fever, dengue fever, poliomyelitis, influenza, AIDS. The list of diseases caused by viruses reads like a catalogue of human misery. The scientists who deciphered the virus's secrets were literally groping in the dark, trying to understand something they could not see, and, for many years, could not even imagine. Viruses exist in a strange realm between the living and the non-living. They do not possess all of the required molecular machinery to reproduce, but once they infect animals, plants, fungi, or bacteria, they can hijack their hosts to generate numerous viral copies. Some viruses may coax their host cells into uncontrolled multiplication, leading to cancer. Given that an average virus is about 1/100th the size of an average bacterium, we now know that most viruses are too small to be visible under an ordinary light microscope. The virions, virus particles, consist of genetic material such as DNA or RNA and an outer protein coating. Some viruses also have an envelope of lipids, small organic molecules, outside a host cell. In 1892, Russian biologist Dmitry Ivanovsky took one of the early steps toward understanding viruses when he attempted to understand the cause of tobacco mosaic disease, which destroys tobacco leaves. He filtered an extract of crushed diseased leaves using a fine porcelain filter to trap all bacteria. To his surprise, the fluid that had flowed through the filter was still infectious. However, Ivanovsky never understood the viral cause, believing that toxins or bacterial spores might be the causative agent. In 1898, Dutch microbiologist Martinus Beijerinck performed a similar experiment and believed this new infectious agent was naturally liquid, referring to it as soluble living germs. Later, researchers grew viruses in media containing guinea pig cornea tissue, minced hen kidneys, and fertilized chicken eggs. The electron microscope finally allowed researchers to see viruses in the 1930s. Upon seeing her husband's X-ray image of her hand, Wilhelm Röntgen's wife shrieked in terror and thought that the rays were evil harbingers of death, writes author Kendall Haven. Within a month, Wilhelm Röntgen's X-rays were the talk of the world. Skeptics called them death rays that would destroy the human race. Eager dreamers called them miracle rays that could make the blind see again and beam diagrams straight into a student's brains. However, for physicians, X-rays marked a turning point in treating the sick and wounded. Wilhelm Röntgen, a German physicist, was experimenting with a cathode ray tube on November 8, 1895, when he discovered that, despite the tube's heavy cardboard covering, a discarded fluorescent screen lit over a meter away when he switched on the tube. He realized that some form of invisible ray was coming from the tube, and he soon found that it could penetrate various materials, including wood, glass, and rubber. He saw a shadowy image of his bones when he placed his hand in the path of the invisible rays. He called the rays X-radiation because they were unknown and mysterious then, and he continued his experiments in secrecy to better understand the phenomena before discussing them with other professionals. Röntgen would win the first Nobel Prize for his systematic study of X-rays. Physicians quickly made use of X-rays for diagnoses. Still, the precise nature of X-rays was not fully elucidated until around 1912, when Max von Laue used X-rays to create a diffraction pattern of a crystal, which verified that X-rays were electromagnetic waves, like light, but of a higher energy and a shorter wavelength that was comparable to the distance between atoms in molecules. Numerous fields today utilize X-rays, from X-ray crystallography to X-ray astronomy, where X-ray detectors on satellites study X-ray emissions from outer space sources. Mathematician Don Zagier has commented that, despite their simple definition and role as the building blocks of the natural numbers, the prime numbers grow like weeds among the natural numbers, and nobody can predict where the next one will sprout. Even more astonishing, the prime numbers exhibit stunning regularity. There are laws governing their behavior, and they obey these laws with almost military precision. Consider Pn, the number of primes less than or equal to a given number n. In 1792, when he was only 15 years old, Carl Gauss became fascinated by the occurrence of prime numbers, and he proposed that Pn was approximately equal to n ln n, where ln is the natural logarithm. One consequence of the prime number theorem is that the nth prime number is approximately equal to n, with the relative error of this approximation approaching 0 as n approaches infinity. Gauss later refined his estimate to Pn, ln, where ln is the integral from 2 to n of dx ln x. Finally, 1896, French mathematician Jacques Hadamard and Belgian mathematician Charles-Jean de la Vallée-Poussin independently proved Gauss's theorem. Based on numerical experiments, mathematicians conjectured that Pn was always somewhat less than ln. English mathematician G.H. Hardy once described skews as the largest number which has ever served any definite purpose in mathematics, although it has since lost this lofty accolade. Around 1950, Paul Erdős and Atle Selberg discovered an elementary proof of the prime number theorem, a proof that uses only real numbers. Picture popcorn popping on your stove to understand the behavior of radioactive nuclei, the central regions of atoms. Kernels appear randomly over several minutes and a few don't pop. Similarly, most familiar nuclei are stable and essentially the same as they were centuries ago. However, as the nuclei disintegrate, other nuclei become unstable and spew fragments. Radioactivity is the emission of such particles. The discovery of radioactivity is usually associated with French scientist Henri Becquerel's 1896 observations of phosphorescence in uranium salts. Roughly a year before Becquerel's discovery, German physicist Wilhelm Röntgen discovered X-rays while experimenting with electrical discharge tubes, and Becquerel was curious to see if phosphorescent compounds that emit visible light after being stimulated by sunlight or other excitation waves, might also produce X-rays. Becquerel placed uranium potassium sulfate on a photographic plate wrapped in black paper. He wanted to see if this compound would phosphoresce and emit X-rays when light was stimulated. To Becquerel's surprise, the uranium compound darkened the photographic plate even when the packet was in a drawer. Uranium seemed to be emitting some penetrating rays. In 1898, physicists Marie and Pierre Curie discovered two new radioactive elements, polonium and radium. Regrettably, some physicians did not immediately recognize the dangers of radioactivity, leading them to prescribe radium enema treatments, among other dangerous remedies. Later, Ernest Rutherford and Frederick Soddy discovered that these elements were transforming into other elements in the radioactive process. Scientists have identified three common forms of radioactivity. Alpha particles, bare helium nuclei. Beta rays, high-energy electrons. Gamma rays, high-energy electromagnetic rays. Today, as noted by author Stephen Battersby, scientists use radioactivity for medical imaging, tumor killing, dating ancient artifacts, and food preservation. The physicist J.J. Thomson loved to laugh, writes author Josepha Sherman. But he was also clumsy. Test tubes broke in his hands and experiments refused to work. Fortunately, Thomson persevered and confirmed the suspicions of Benjamin Franklin and other physicists that tiny electrical charge units produced electrical effects. In 1897, J.J. Thomson identified the electron as a distinct particle with a much smaller mass than the atom. His experiments employed a cathode ray tube, an evacuated tube in which a beam of energy travels between a positive and negative terminal. Although no one was sure what cathode rays were at the time, Thomson was able to bend the cathode rays using a magnetic field. By observing how the cathode rays moved through electric and magnetic fields, He determined that the particles were identical and did not depend on the metal that emitted them. Also, the particles all had the same ratio of electric charge to mass. Others had made similar observations, but Thomson was among the first to suggest that these corpuscles were the carriers of all forms of electricity and a basic matter component. Many sections of this book discuss the various properties of electrons. Today, we know that the electron is a subatomic particle with a negative electric charge and a mass that is 1/1136 of the mass of a proton. An electron in motion generates a magnetic field. The Coulomb force, an attractive force between the positive proton and the negative electron, binds electrons to atoms. When atoms share two or more electrons, they can form chemical bonds. According to the American Institute of Physics, modern ideas and technologies based on the electron, which led to the television, the computer, and much else, evolved through many difficult steps. Many others followed Thomson's careful experiments and adventurous hypotheses with crucial experimental and theoretical work, providing us with a new perspective, a view from inside the atom. According to author Catherine Reif, the Austrian physician Sigmund Freud explored the human mind more thoroughly than anyone before him. He pioneered a new method for diagnosing and treating mental illness, which he called psychoanalysis. He communicated with him, and more importantly, he listened to him. Freud emphasized the importance of unconscious mental processes in shaping human behavior and emotions, and he encouraged his patients to freely associate and speak about images from fantasies and dreams. He encouraged patients to act as though they were travelers, sitting next to the window of a railway carriage and describing to someone outside the carriage the changing views seen outside. When waiting for his patients' words to reveal hidden messages, Freud often felt like an archaeologist unearthing precious relics in ancient cities. He aimed to interpret unconscious conflicts that caused harmful symptoms, thereby giving the patients insight and resolutions to their problems, including abnormal fears or obsessions. The interpretation of dreams, published in 1899, was his greatest work. In general, Freud often suggested that patients' repressed sexual fantasies and early childhood experiences played an important role in later dysfunctional behavior. His most famous psychoanalytic model divided the mind into three separate parts. The ID is preoccupied with fundamental desires like sexual fulfillment. The superego is primarily focused on societal norms and ethical principles. The conscious mind, the ego, drives our choices by balancing the ID and superego. Although it is still difficult to discern what fraction of his often controversial ideas will ultimately be considered correct or even useful, his ideas on psychology have completely revolutionized our conception of the human mind, according to author Michael Hart. Rather than condemn or ridicule those with behavioral anomalies, Freud sought understanding. Psychiatrist Anthony Storr writes, Freud's technique of listening to distressed people over long periods, rather than giving them orders or advice, has formed the foundation of most modern forms of psychotherapy, with benefits to both patients and practitioners. Quantum mechanics is magic, writes quantum physicist Daniel Greenberger. Quantum theory, which suggests that matter and energy have the properties of particles and waves, originated in pioneering research concerning hot objects that emit radiation. For example, imagine the coil on an electric heater that glows brown and then red as it gets hotter. The blackbody radiation law, proposed by German physicist Max Planck in 1900, quantifies the amount of energy emitted by blackbodies at a particular wavelength. Blackbodies emit and absorb the maximum possible amount of radiation at any given wavelength and temperature. Many of the objects we encounter every day emit a large portion of their radiation spectrum in the infrared or far infrared portion, which is not visible to our eyes. A blackbody's amount of thermal radiation varies with frequency and temperature. However, as a body's temperature increases, the dominant portion of its spectrum shifts, allowing us to see a glow from the object. A large, hollow, rigid object like a sphere can approximate a blackbody in the laboratory by poking a hole in its side. Radiation entering the hole reflects off the inner walls, dissipating with each reflection as the walls absorb the radiation. When the radiation exits through the same hole, its intensity is negligible. Thus, this hole acts as a black body. Planck modeled black bodies' cavity walls as tiny electromagnetic oscillators. He posited that oscillators' energy is discrete and could assume only certain values. These oscillators emit energy into the cavity and absorb it via discrete jumps or quanta packages. Planck's quantum approach, which involved discrete oscillator energies for theoretically deriving his radiation law, led to his 1918 Nobel Prize. Today, we know that the universe was a near-perfect blackbody right after the Big Bang. In 1860, German physicist Gustav Kirchhoff introduced the term blackbody. Numerous studies of the subatomic world have demonstrated that particles like electrons or photons, packets of light, are not like objects we interact with in our everyday lives. Depending on the experiment or observed phenomenon, these entities appear to possess characteristics of both waves and particles. Welcome to the strange realm of quantum mechanics. In 1924, French physicist Louis-Victor de Broglie proposed that particles of matter could also be considered waves and possess properties commonly associated with waves, including a wavelength, the distance between successive wave crests. In fact, all bodies have a wavelength. In 1927, American physicists Clinton Davison and Lester Germer demonstrated electrons' wave nature by diffracting and interfering like light. De Broglie's famous relationship showed that the wavelength of a matter wave is inversely proportional to the particle's momentum, generally speaking, mass times velocity, particularly L/hp. Here, L is the wavelength, p is the momentum, and h is Planck's constant. According to author Joanne Baker, using this equation, it is possible to show that bigger objects like ball bearings and badgers have minuscule wavelengths, too small to see, so we cannot spot them behaving like waves. A tennis ball flying across a court has a wavelength of 1034 meters, much smaller than a proton's width, 1015 meters. An ant's wavelength is larger than that of a human. Since the original Davison-Germer experiment for electrons, scientists have confirmed the de Broglie hypothesis for other particles like neutrons and protons. In 1999, they even confirmed it for entire molecules, like buckyballs, which are soccer ball-shaped molecules made of carbon atoms. In his PhD thesis, de Broglie advanced his idea, but it was so radical that his thesis examiners initially wondered if they should approve it. He later won the Nobel Prize for this work. Imagine people beginning to fill the seats in a baseball stadium, starting at the rows nearest the playing field. This is a metaphor for electrons filling the orbitals of an atom. In baseball and atomic physics, rules state that many entities, such as electrons or people, can fill the allotted areas. After all, it would be quite uncomfortable if multiple people attempted to squeeze into a small seat. Pauli's exclusion principle, PEEP, explains why matter is rigid and two objects cannot occupy the same space. That's why we don't fall through the floor. Neutron stars resist collapsing under their incredible mass. Specifically, PEP states that no pair of identical fermions, such as electrons, protons, or neutrons, can simultaneously occupy the same quantum state, including a fermion's spin. For example, electrons occupying the same atomic orbital must have opposite spins. Once two electrons with opposite spins occupy an orbital, no more electrons can enter until one departs. PEP is well tested and one of the most important principles in physics. Author Michela Massimi states, "From spectroscopy to atomic physics, from quantum field theory to high-energy physics, there is hardly another scientific principle that has more far-reaching implications than Pauli's exclusion principle." PEEP allows one to determine or understand the electronic configurations underlying the classification of chemical elements in the periodic table and atomic spectra. Pauli introduced this principle early in 1925, before the advent of modern quantum theory or the concept of electron spin. His motivation was simple. There had to be something to prevent all the electrons in an atom from collapsing down to a single lowest state. Pauli's exclusion principle keeps electrons, and other fermions, from invading each other's space. Schrödinger's wave equation enabled scientists to make detailed predictions about how matter behaves while being able to visualize the atomic systems under study, writes physicist Arthur Phi Miller. Schrödinger apparently developed his formulation while vacationing at a Swiss ski resort with his mistress, who seemed to catalyze his intellectual and erotic outburst, as he called it. The Schrödinger wave equation describes the ultimate reality regarding wave functions and probabilities. Given the equation, we can calculate a particle's wave function. Here we need not worry about the details of this formula, except perhaps to note that psi RT is the wave function, which is the probability amplitude for a particle to have a given position r at any given time. T2 is used to describe how psi RT changes in space. VI r denotes the particle's potential energy at each position r. Just as an ordinary wave equation describes the progression of a ripple across a pond, Schrödinger's wave equation describes how a probability wave associated with a particle, e.g., an electron, moves through space. The wave's peak corresponds to where the particle is most likely to be. The equation was also useful in understanding the energy levels of electrons in atoms, and it became one of the foundations of quantum mechanics, the physics of the atomic world. Although describing a particle as a wave may seem odd, such strange dualities are necessary in the quantum realm. For example, light can act as either a wave or a particle, a photon, and particles such as electrons and protons can act as waves. As another analogy, consider electrons in an atom as waves on a drumhead, with the vibration modes of the wave equation associated with different energy levels of atoms. Note that Werner Heisenberg, Max Born, and Pascual Jordan developed matrix mechanics in 1925 to interpret certain particles' properties in terms of matrices. This formulation is equivalent to the Schrödinger wave formulation. Danish physicist Niels Bohr developed a concept that he referred to as complementarity in the late 1920s, while trying to make sense of the mysteries of quantum mechanics, which suggested, for example, that light sometimes behaved like a wave and at other times like a particle. For Bohr, writes author Louisa Gilder, complementarity was an almost religious belief that the paradox of the quantum world must be accepted as fundamental, not to be solved or trivialized by attempts to find out what's really going on down there. Bohr used the word in an unusual way. The complementarity of waves and particles, for example, or of position and momentum, meant that when one existed fully, its complement did not exist at all. Bohr himself, in a 1927 lecture in Como, Italy, said that waves and particles are abstractions, their properties being definable and observable only through their interactions with other systems. Sometimes the physics and philosophy of complementarity overlap with artistic theories. K.C. Kohler, a science writer, states that Bohr's fascination with cubism, particularly the idea that an object can transform into multiple forms, such as a face, a limb, or a fruit bowl, is well known. Bohr formulated his philosophy of complementarity, demonstrating the ability of an electron to transform and manifest as either a wave or a particle. Like cubism, complementarity allowed contradictory views to coexist in the same natural frame. Bohr thought viewing the subatomic world from our everyday perspective was inappropriate. In our description of nature, Bohr wrote, the purpose is not to disclose the real essence of phenomena, but only to track down, as far as it is possible, relations between the manifold aspects of experience. In 1963, physicist John Wheeler expressed the importance of this principle. Bohr's principle of complementarity is the most revolutionary scientific concept of this century and the heart of his 50-year search for the full significance of the quantum idea. The food chain concept originated with Al-Jahiz, a 9th-century Arabic author of 200 books on various subjects, including grammar, poetry, and zoology. In his zoology work, he discussed a struggle for existence among animals who hunt to obtain food and are, in turn, hunted. Charles Elton, an Oxford faculty member, was among the most important animal ecologists of the 20th century. In his classic 1927 text, Animal Ecology, Elton laid out the basic principles of modern ecology, including, rather explicitly, food chains and food webs, which are now central themes in ecology. At its simplest level, a food cycle follows a linear relationship from the base of the food chain, a species that eats no other, typically a plant, to the final predator or ultimate consumer, typically 3 to 6 feeding levels in length. Elton recognized that this simple food chain depiction was a gross oversimplification of who eats whom. The food chain failed to account for real ecosystems where there are multiple predators and prey, and a given animal might consume other animals if the preferred prey was unavailable. Furthermore, some carnivores are omnivores and eat plant material. Conversely, herbivores occasionally eat meat. The food web, now referred to as the food chain, represents these highly complex interrelationships. Raymond Lindemann postulated in 1942 that trophic dynamics, or the effective transfer of energy from one part of the ecosystem to another, limit the number of levels in a food chain. After eating, the consumer's body stores energy and only allows it to travel in one direction. Much of that energy is lost as heat when the food is utilized for basic needs, and the remainder is eliminated as waste material. At the next higher trophic, feeding level, only about 10% of the consumed energy remains available. Therefore, energy transmission decreases with each successive level up the chain, resulting in food chains rarely surpassing 4 to 5 feeding levels. Uncertainty is the only certainty there is, wrote mathematician John Allen Paulos, and knowing how to live with insecurity is the only security. The Heisenberg uncertainty principle states that a particle's position and velocity cannot simultaneously be known with high precision. In other words, the more precise the measurement of position, the more imprecise the measurement of momentum, and vice versa. The uncertainty principle becomes significant at the small scales of atoms and subatomic particles. Before the discovery of this law, most scientists believed that the accuracy of the instruments solely limited the precision of any measurement. German physicist Werner Heisenberg hypothetically suggested that even if we could construct an infinitely precise measuring instrument, we still could not accurately determine a particle's position and momentum, mass x velocity. The principle does not concern the degree to which a particle's position measurement may disturb its momentum. We could measure a particle's position with high precision, but consequently, we could know little about the momentum. For those scientists who accept the Copenhagen interpretation of quantum mechanics, the Heisenberg uncertainty principle means that the physical universe literally does not exist in a deterministic form, but is rather a collection of probabilities. Similarly, an infinitely precise measurement cannot predict the path of an elementary particle, such as a photon, even in theory. In 1935, Heisenberg chose to replace his former mentor, Arnold Sommerfeld, at the University of Munich. Alas, the Nazis required that German physics replace Jewish physics, which included quantum theory and relativity. Consequently, the Nazis blocked Heisenberg's appointment to Munich, despite his non-Jewish heritage. During World War II, Heisenberg led the unsuccessful German nuclear weapons program. Today, science historians debate whether the program failed because of a lack of resources, a lack of the right scientists on his team, Heisenberg's lack of desire to give such a powerful weapon to the Nazis, or other factors. Animals communicate with one another to locate food, mate, or signal an alarm in the presence of threats in their environment. Various animals use pheromones to facilitate various phases of their mating behavior. Not all communication occurs between members of the same animal species, such as our pets' facial expressions and body language. Skunks use their odorous spray as a highly effective defensive weapon, so pungent that human noses can detect it at downwind distances of 1 mile, 1.6 kilometers. Vertebrates are not the only animals that communicate, with insects exhibiting some of the most fascinating examples. Nobel laureate Karl von Frisch, an Austrian ethnologist at the University of Munich, conducted pioneering studies on insect communications in the 1920s. He observed that European honeybee, Apis mellifera, foragers use a distinctive dance language to inform other bees in the hive about the direction and distance of food. When food is close to the hive, less than 160-320 feet, 50-100 meters, the forager performs a round dance in which they execute tight circles, whereas a waggle dance, resembling a figure-8 movement, indicates food at a distant location. European honeybees also use a complex chain of communication modes that involve all 5 senses in a fascinating courtship ritual, with each signaling and triggering a subsequent behavior by the partner. The male visually identifies the female and turns toward her. The male's olfactory system detects a chemical that the female releases. He approaches the female and taps her with his limb, picking up the chemical. In response, the male extends and vibrates his wings, producing a courtship song, a form of auditory communication. Only after this entire sequence is successively and successfully completed will the female allow the male to perform copulation. As discussed in the entry on antimatter, physics equations can sometimes give birth to ideas or consequences that the equation's discoverer did not expect. According to physicist Frank Wilczek in his essay on the Dirac equation, the power of these kinds of equations can seem magical. In 1927, Paul Dirac attempted to find a version of Schrödinger's wave equation consistent with special relativity principles. In 1928, Paul Dirac wrote the Dirac equation, describing electrons and other elementary particles in a manner consistent with quantum mechanics and the special theory of relativity. The equation predicts the existence of antiparticles and, in some sense, foretells their experimental discovery. This feature led to the discovery of the positron, the electron's antiparticle, a fine example of mathematics' usefulness in modern theoretical physics. In this equation, m is the rest mass of the electron, h is the reduced Planck's constant, 1.054 x 10^34 Js, c is the speed of light, p is the momentum operator, x and t are the space and time coordinates, and 6ext is a wave function. A is a linear operator that acts on the wave function. Physicist Freeman Dyson has lauded this formula, representing a significant stage in humanity's grasp of reality. Sometimes the discovery of a single basic equation suddenly advances the understanding of a whole field of science, he writes. Thus, the Schrödinger equation in 1926 and the Dirac equation in 1927 brought a miraculous order into the previously mysterious atomic physics processes. 2 lines of algebraic symbols simplified the bewildering complexities of chemistry and physics. Reflecting on his discovery later in life, Scottish biologist Alexander Fleming recalled, "When I woke up just after dawn on September 28, 1928, I certainly didn't plan to revolutionize all medicine by discovering the world's first antibiotic or bacteria killer, but I suppose that was exactly what I did." When Fleming returned from a vacation, he noticed mold had developed on his contaminated culture plate of the bacterium Staphylococcus. He also observed the inhibition of bacterial growth near the mold, leading him to deduce that the mold was secreting a substance that suppressed bacterial growth. He soon grew a pure mold culture in broth, determined the mold to be of the Penicillium genus and referred to the antibiotic substance in the broth as penicillin. Interestingly, many ancient societies had noticed that mold could serve as a remedy, and Irish physicist John Tyndall even demonstrated the antibacterial action of the penicillium fungus in 1875. However, Fleming was probably the first to suggest that this mold secreted an antibacterial substance and isolated it. Later studies showed that penicillin works by weakening the cell walls of bacteria. In 1941, Australian pharmacologist Howard Florey, German biochemist Ernst Chain, and English biochemist Norman Heatley, while working together in England, were finally able to turn penicillin into a usable drug, showing that it cured infections in mice and people. The US and British governments were determined to produce as much penicillin as possible to help their soldiers during World War II, and a moldy cantaloupe in Peoria, Illinois, produced more than 2 million doses before 1944. Penicillin was soon used to defeat major bacterial diseases such as blood poisoning, pneumonia, diphtheria, scarlet fever, gonorrhea, and syphilis. Unfortunately, antibiotic-resistant bacterial strains have evolved, necessitating the quest for additional antibiotics. Molds are not the only producers of natural antibiotics. For example, the bacterium Streptomyces is the source of streptomycin and tetracyclines. Penicillin and these later discovered antibiotics sparked a revolution in the disease fight. Arguably the most important cosmological discovery ever made, writes cosmologist John P. Huettrer, is that our universe is expanding. It stands alongside the Copernican principle, that there is no preferred place in the universe, and Olber's paradox, that the sky is dark at night, as one of the cornerstones of modern cosmology. It forced cosmologists to consider dynamic models of the universe and also implies the existence of a timescale or age for the universe. Edwin Hubble's estimates of distances to nearby galaxies primarily made it possible. In 1929, American astronomer Edwin Hubble discovered that the greater the distance a galaxy is from an observer on the Earth, the faster it recedes. The distances between galaxies, or galactic clusters, continuously increase. Therefore, the universe expands. For many galaxies, the velocity, e.g., the movement of a galaxy away from an observer on the Earth, can be estimated from the redshift of a galaxy, which is an observed increase in the wavelength of electromagnetic radiation received by a detector on the Earth compared to that emitted by the source. Such redshifts occur because galaxies are moving away from our own galaxy at high speeds due to space's expansion. The relative motion of the light source and the receiver causes a change in the light's wavelength. Other methods also exist for determining the velocity of faraway galaxies. Objects dominated by local gravitational interactions, like stars within a single galaxy, do not exhibit this apparent movement away from one another. Although an observer on Earth finds that all distant galactic clusters are flying away from Earth, our location in space is not special. An observer in another galaxy would also see the galactic clusters flying away from the observer's position because all of space is expanding. This is one of the main lines of evidence for the Big Bang, from which the early universe evolved, and the subsequent expansion of space. Austrian mathematician Kurt Gödel was an eminent mathematician among the most brilliant logicians of the 20th century. His incompleteness theorem has vast implications, affecting mathematics, computer science, economics, and physics. When Gödel was at Princeton University, Albert Einstein was one of his closest friends. subject in his book, Reflections on Kurt Gödel. The impact of Gödel's scientific ideas and philosophical speculations has been increasing, and the value of their potential implications may continue to increase. It may take centuries to confirm or refute some of his larger conjectures. Douglas Hofstadter notes that Gödel's second theorem also suggests the inherent limitations of mathematical systems and implies that the only versions of formal number theory that assert their own consistency are inconsistent. In 1970, Gödel's mathematical proof of the existence of God began to circulate among his colleagues. The proof was less than a page long and caused quite a stir. Toward the end of his life, Gödel was paranoid and felt that people were trying to poison him. He stopped eating and died in 1978. During his life, he also suffered from nervous breakdowns and hypochondria. Joanne Baker writes, "Antimatter drives often power fictional spaceships, but antimatter itself is real and even artificially created on Earth. The mirror image form of matter, antimatter, cannot coexist with matter for long. Both annihilate in a flash of energy if they come into contact. The very existence of antimatter points at deep symmetries in particle physics." Paul Dirac, a British physicist, once remarked that the abstract mathematics we study now gives us a glimpse of physics in the future. Indeed, his 1928 equations on electron motion foretold the discovery of antimatter. According to the formulas, an electron must have an antiparticle with the same mass but a positive electrical charge. In 1932, Carl Anderson, a US physicist, observed this new particle experimentally and named it the positron. Berkeley Bevatron, a particle accelerator, produced the antiproton in 1955. In 1995, physicists created the first anti-hydrogen atom at the CERN research facility in Europe. CERN, Organisation Européenne pour la Recherche Nucléaire, or the European Organization for Nuclear Research, is the largest particle physics laboratory in the world. Antimatter-matter reactions have practical applications today in positron emission tomography, PET. This medical imaging technique involves the detection of gamma rays, high-energy radiation, emitted by a positron-emitting tracer radionuclide, an atom with an unstable nucleus. Modern physicists continue to offer hypotheses to explain why the observable universe appears nearly entirely composed of matter, not antimatter. Could regions of the universe exist in which antimatter predominates? Upon casual inspection, antimatter would be almost indistinguishable from ordinary matter. Physicist Michio Kaku writes, "You can form anti-atoms out of anti-electrons and anti-protons. Theoretically, even anti-people and anti-planets are possible. However, antimatter will annihilate into a burst of energy upon contact with ordinary matter. Anyone holding a piece of antimatter in their hands would immediately explode with the force of thousands of hydrogen bombs." James Chadwick's road to the discovery of the neutron was long and tortuous, writes chemist William H. Cropper. Because they carried no electrical charge, neutrons did not leave observable trails of ions as they passed through matter and left no tracks in Wilson's cloud chamber. To the experimenter, they were invisible. Physicist Mark Oliphant states that Chadwick's persistent search, unlike radioactivity and X-rays, led to the discovery of the neutron. Chadwick intuitively sensed the neutron's existence and persistently pursued its discovery. The neutron is a subatomic particle that is part of every atomic nucleus except for ordinary hydrogen. It has no net electric charge, and its mass is slightly greater than a proton's. Similar to the proton, it consists of 3 quarks. When the neutron is inside the nucleus, the neutron is stable. However, free neutrons undergo beta decay, a type of radioactive decay, and have a mean lifetime of approximately 15 minutes. Nuclear fission and fusion reactions produce free neutrons. Irene Joliot. Curie, the daughter of Marie. Curie, the first person to receive 2 Nobel Prizes, and her husband Frédéric Joliot described a mysterious radiation in 1931 that resulted from bombarding beryllium atoms with alpha particles, helium nuclei, which knocked protons loose from hydrogen-containing paraffin. James Chadwick conducted additional experiments in 1932 and proposed that neutrons, uncharged particles approximately the mass of a proton, composed this new kind of radiation. Because the free neutrons are uncharged, electrical fields do not hinder their ability to penetrate deeply into matter. Later, researchers discovered that when bombarded by neutrons, various elements undergo fission, a nuclear reaction that occurs when the nucleus of a heavy element splits into 2 nearly equal smaller pieces. In 1942, US researchers demonstrated that the free neutrons generated during fission could trigger a chain reaction, generate vast amounts of energy, and potentially create atomic bombs and nuclear power plants. Science educators Jeff McNamara and astronomer Ken Freeman argue that the periodic table of elements does not accurately depict the composition of the universe. We now know that dark matter and energy, comprising about 96% of the universe, defy a brief description. Regardless of its composition, dark matter fails to emit or reflect enough light or other electromagnetic radiation for direct observation. Scientists infer its existence from gravitational effects on visible matter, such as galaxies' rotational speeds. Standard elementary particles like protons, neutrons, electrons, and known neutrinos probably comprise only a small portion of dark matter. Instead, hypothetical constituents with exotic names like sterile neutrinos, axions, and WIMPs, weakly interacting massive particles, including neutralinos, do not interact with electromagnetism and are difficult to detect. The hypothetical neutralinos are similar to neutrinos, but heavier and slower. Theorists also consider the following possibilities for dark matter: gravitons, hypothetical particles that transmit gravity. Neighboring universes are leaking into ours. If our universe is on a membrane floating within a higher dimensional space, ordinary stars and galaxies on nearby membrane sheets may explain dark matter. In 1933, the astronomer Fritz Zwicky provided evidence for the existence of dark matter through his studies of the motions of the edges of galaxies, which suggested a significant amount of galactic mass was undetectable. In the late 1960s, astronomer Vera Rubin showed that most stars in spiral galaxies orbit at approximately the same speed, which implied the existence of dark matter beyond the locations of stars in the galaxies. In 2005, astronomers from Cardiff University believed they had discovered a galaxy in the Virgo cluster made almost entirely of dark matter. Freeman and McNamara write, "Dark matter provides a further reminder that we humans are not essential to the universe. We do not share the same composition with the majority of the universe. Our universe is made of darkness." Unfortunately, 1933 was the first industrial polyethylene synthesis, not the first reliable one. The German chemist Hans von Pechmann accidentally prepared it in 1898 while working with pure diazomethane. No one was foolhardy enough to work with the explosive and toxic diazomethane on a larger scale, so this remained a chemical footnote until British chemist Reginald Oswald Gibson and British-Canadian physicist Eric Fawcett tried a high-pressure, high-temperature reaction between ethylene gas and benzaldehyde, the same compound that inspired the work of German chemists Friedrich Wöhler and Justus von Liebig on functional groups back in 1832. They found that long chains of CH2 methylene groups composed the white, waxy polymer they produced. Given its resistance to chemicals and solvents and malleability, polymerized ethylene appeared to have potential as a highly useful material. However, getting the reaction to work reproducibly was frustrating until British chemist Michael Wilcox Perrin figured out the right conditions in 1937. As it happened, traces of oxygen caused that first reaction's accidental success, and later routes used small amounts of more reliable free radical initiators under milder conditions. During World War II, the discovery of polyethylene's use as an insulator in electronics, such as radar equipment, led to its secret status. By the war's end, its many forms, hard blocks, thin sheets, and flexible panels, were beginning to gain appreciation. Today, polyethylene is the most common plastic polymer in the world. Polyethylene can exhibit a wide range of properties, from flexible, low-density polyethylene, or LDPE, to rigid, high-density polyethylene, or HDPE, depending on its manufacturing process. Each year, products as diverse as squeeze bottles, trash bags, sporting goods, and toys utilize hundreds of millions of tons of this material. Its research is still ongoing, an impressive performance for something whose first preparations were all mistakes. Stars are born when a large amount of hydrogen gas starts to collapse in on itself due to gravitational attraction. As the star coalesces, it heats up, produces light, and forms helium. Eventually, the star runs out of hydrogen fuel, starts to cool, and enters one of several possible graveyard states, such as a black hole or one of its crushed cousins, such as a white dwarf, for relatively small stars, or a neutron star. In particular, after a massive star has finished burning its nuclear fuel, the central region collapses due to gravity, and the star undergoes a supernova explosion, blowing off its outer layers. This gravitational collapse may create a neutron star, made almost entirely of uncharged subatomic particles called neutrons. The Pauli exclusion principle states that repulsion between neutrons prevents a neutron star from achieving the complete gravitational collapse of a black hole. A typical neutron star has a mass between 1.4 and 2 times that of our Sun, but a radius of only around 7.5 miles, 12 kilometers. Interestingly, neutron stars are formed from neutronium, an extraordinary material so dense that a sugar cube could contain the entire human population's crushed mass. Pulsars are rapidly rotating, highly magnetic neutron stars that send out steady electromagnetic radiation that arrives at the Earth as pulses due to the star's rotation. The pulses are at intervals ranging from milliseconds to several seconds. The fastest millisecond pulsars spin over 700 times per second. In 1967, graduate student Jocelyn Bell Burnell discovered pulsars, radio sources that appeared to blink constantly. Only a year after the discovery of the neutron, astrophysicists Fritz Zwicky and Walter Baade proposed the existence of a neutron star in 1933. In the novel Dragon's Egg, creatures live on a neutron star, where the gravity is such that mountain ranges are about a centimeter high. Quantum entanglement, QE, refers to an intimate connection between quantum particles, such as between 2 electrons or 2 photons. Once a pair of particles entangles, any change to one instantly reflects in the other, regardless of the distance between them, be it inches or interplanetary distances. This entanglement is so counterintuitive that Albert Einstein referred to it as spooky and thought that it demonstrated a flaw in quantum theory. Particularly the Copenhagen interpretation that suggested quantum systems in several contexts existed in a probabilistic limbo until observed and then reached a definite state. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper on their famous EPR paradox. Imagine 2 particles emitted by a source, so their spins are in a quantum superposition of opposite states labeled plus and. Neither particle has a definite spin before measurement. The particles fly apart, one going to Florida and the other to California. According to QE, if scientists in Florida measure the spin and find a plus, the California particle instantly assumes the state, even though the speed of light prohibits faster than light, FTL information communication. However, it is important to note that no FTL information communication has taken place. Florida cannot use entanglement to send messages to California because it does not manipulate its particle's spin, which has a 50-50 chance of being in a plus or minus state. In 1982, physicist Alain Aspect conducted experiments on oppositely directed photons emitted in a single event from the same atom, thereby confirming the photon pair's correlation. He demonstrated that even when the particle pair separated by an arbitrarily large distance, the instantaneous connection in the EPR paradox occurred. Today, quantum cryptography investigates quantum entanglement to send impenetrable messages without leaving traces. Researchers are now developing simple quantum computers to perform calculations in parallel and faster than traditional computers. Schrödinger's cat reminds me of a ghost or maybe a creepy zombie, a creature that appears alive and dead simultaneously. In 1935, Austrian physicist Erwin Schrödinger published an article on this extraordinary paradox, which has striking consequences that continue to mystify and concern scientists. Schrödinger was upset about the recently proposed Copenhagen interpretation of quantum mechanics, which stated, in essence, that a quantum system, e.g., an electron, exists as a cloud of probability until an observation is made. On a deeper level, the proposal implied that determining the precise actions of atoms and particles when they remain unobserved is pointless. The observer, in a sense, shapes reality. The system assumes all possibilities before observation. What could this mean for our everyday lives? Imagine placing a live cat in a box that contains a radioactive source, a Geiger counter, and a sealed glass flask filled with deadly poison. When radioactive decay occurs, the Geiger counter measures the event, triggering a mechanism that releases the hammer, shattering the flask, and releasing the poison that kills the cat. Quantum theory predicts a 50% probability of emitting one decay particle every hour. An hour later, the cat's survival was equal. According to some flavors of the Copenhagen interpretation, the cat seemed alive and dead, a mixture of two states called a superposition of states. Some theorists suggested that if you open the box, observation collapses the superposition, making the cat either alive or dead. Schrödinger said that his experiment demonstrated the invalidity of the Copenhagen interpretation, and Albert Einstein agreed. This thought experiment sparked many questions. What is a valid observer? The Geiger counter? A fly? Could the cat observe itself and collapse into its own state? What does the experiment really say about the nature of reality? Brilliant mathematician and computer theorist Alan Turing underwent forced human guinea pig experiments and drug trials to reverse his homosexuality. This persecution occurred despite the fact that his code-breaking work helped shorten World War II and led to his Order of the British Empire Award. When Turing called the police to investigate a burglary at his home in England, a homophobic police officer suspected that Turing was homosexual. The police forced Turing to choose between a year in jail or experimental drug therapy. Turing consented to undergo a year-long injection of estrogen hormone to evade imprisonment. His death at age 42, 2 years after his arrest, was a shock to his friends and family. Turing was found in bed. The autopsy indicated cyanide poisoning. Perhaps he had committed suicide, but to this day we are not certain. Many historians consider Turing the father of modern computer science. In his landmark paper, On Computable Numbers with an Application to the Decisions Problem, written in 1936, he proved that Turing machines, abstract symbol manipulating devices, would be capable of performing any conceivable mathematical problem that is represented as an algorithm. Turing machines help scientists better understand the limits of computation. Turing is also the originator of the Turing test, which caused scientists to think more clearly about what it means to call a machine intelligent, and whether computers may one day think. Turing believed that machines would eventually be able to pass his test by demonstrating they could converse with people in such a natural way that people could not tell if they were talking to a machine or a human. In 1939, Turing invented an electromechanical machine that could help break the Nazi codes produced by their Enigma code machine. Mathematician Gordon Welchman enhanced Turing's machine, known as the Bomber, making it the primary tool for deciphering Enigma communications. Every living creature needs energy, and they all use the same molecule to carry it. Adenosine triphosphate, ATP, discovered in 1929 by German chemist Karl Lohmann, working with Otto Fritz Meyerhoff. ATP has a phosphate bond that requires a lot of energy. When that bond cleaves, it gives back that energy. German-American biochemist Fritz Albert Lippmann proposed in 1941 that the molecule is a storable form of power, ready on demand. Throughout your body, billions of adenosine diphosphates and triphosphates are shuttling back and forth, providing chemical energy like so many battery packs to all sorts of proteins. The ATP binding pockets built into them are a standardized motif that appears repeatedly. British biochemist Peter Mitchell discovered the enzyme ATP synthase, which American and British biochemists Paul Boyer and John Walker further explained, as enabling cells to continuously produce ATP in specialized mitochondria structures. These resemble bacteria, and that's no accident. Mitochondria appear to have been bacteria at some point in the distant evolutionary past, moving into early cells and making a home. They're now specialized ATP factories. German-born British biochemist Hans Adolf Krebs, building on the work of Hungarian physiologist Albert Szent-Györgyi of vitamin C fame, worked out the first part of their chemistry in 1937. The reaction cycle begins with citric acid, which is regenerated in the final step before continuing. Along the way, the breakdown of carbohydrates and lipids produces the two-carbon building block acetate, which consumes and releases carbon dioxide. The products of the Krebs cycle go straight into another series of enzyme reactions, called oxidative phosphorylation, which produce ATP while using oxygen. You store the food you eat, the oxygen you breathe, and the carbon dioxide you exhale in the non-stop furnaces of the mitochondria. The eerie behavior of superfluids, like some living, creeping liquid out of a science fiction movie, has intrigued physicists for decades. Placing liquid helium in a superfluid state in a container causes it to climb up the walls and exit the container. Furthermore, spinning the container does not cause the superfluid to move. It seems to seek out and penetrate microscopic cracks and pores, making traditionally adequate containers leaky for superfluids. Place your coffee cup on the table with the liquid still spinning inside. After a few minutes, the coffee will still be there. If you did this with superfluid helium and your ancestors returned in 1,000 years to view the cup, the superfluid might still be spinning. Several substances exhibit superfluidity, but helium-4, a common naturally occurring isotope of helium with 2 protons, 2 neutrons, and 2 electrons, is often the subject of study. Below a very low temperature called the lambda temperature, 455-49 OF 2.17 K, this liquid helium-4 can suddenly flow without any friction. Its thermal conductivity is millions of times higher than that of normal liquid helium, as well as much higher than that of the best metal conductors. Helium I refers to liquids above 2.17 K, while helium-2 refers to liquids below this temperature. Physicists Piotr Kapitsa, John F. Allen, and Don Mizina discovered superfluidity in 1937. In 1938, Fritz London proposed that liquid helium below the lambda point temperature consists of 2 components: a normal fluid exhibiting the helium-1 characteristic, and a superfluid with a viscosity value of 0. The transition from ordinary fluid to superfluid occurs when the constituent atoms begin to occupy the same quantum state and their quantum wave functions overlap. In the Bose-Einstein condensate, the atoms lose their identities and behave as one large, smeared entity. Because the superfluid has no internal viscosity, a vortex formed within the fluid continues to spin forever.